something about the design of clinical trials, specifically allocation of the patients in groups. This is the structure of my presentation, and I will give some motivation. I will cite Basu, a very important statistician. The counter question, how can I justify supposed sampling, has a lot of force in it. The choice of a purpose plan will make a scientist vulnerable to all kinds of open and valid criticism. A way out of the dilemma is to make the plan very proposed, but to leave a tiny bit of randomization in the plan. And Basu says that we need to consider proposed sampling, but insert some randomization in the process. And I will cite Lindley. We discard a possible allocation that the experimenter judges to be free of covariant interference as haphazard. Randomization may be a convenient way of producing haphazard design. We argue that it's the haphazard nature, and not the randomization that's important. It seems therefore that a reasonable approximation to an optimal design will select a haphazard design. And he continues. A detailed basic consideration of possible covariates would almost certainly not be robust, and that the analysis might be sensitive to small changes in judgment about covariates. This sentence is the bigger motivation of this work, but we'll present the study that motivated this work. And this was originated in Protoc at the Psychiatry Institute from USP, and is motivated by a clinical trial with obsessive-compulsive disorder patients. We have a convenient sample there. What is this? The patients come to the hospital looking for treatment, and his patients need to send to some treatment groups weekly because they need treatment. It's not possible to determine the exact sample size because we don't know how much patients you have in the study. And it is known that some variables may influence the treatment response, such as gender or disease severity, and we would like that these variables are equally distributed among the treatment groups. Intentional sampling methods are non-randomized procedures that selects or allocates groups of individuals which propose of meet specific prescribed criteria. Such methods can overcome some of the limitations of standard randomized designs when cost or ethical inherent heritage constraints only limit the use of very small samples. However, intentional or proposed sampling methods pose several interesting questions concerning the statistical inference, and this topic is extensively discussed in Basu and Goshi, Shelder, Brewer and Sundown, and for discussion in Meadow. And this presentation focuses on the sequential allocation methods following the previous research by me and the other authors. Before I introduce the methods, I will need to introduce some topics on compositional models and simplex geometry. We will consider N-1 simplex, a set like this. And the two important transformations, the closer to unity, that is only divided the vector by the sum of his components, and the additive log-rate transformation, that is considered the n-1 first components of the vector divided by the last one, and apply the log in this new vector. I'm going to introduce some operators to power, that's similar to scalar multiplication in this context, interpreted as alpha times repeats the factor of proportional decay rates. The perturbation, or similar to vector summation, that is the closer to unity transformation of the product of each component of each vector. And this perturbation could be interpreted as an effect of proportional decay rates in y over the fractional composition x, and the difference, that is the closer to unity transformation of the ratio of each component of each vector. And we wanted a distance function to consider here that exhibits the invariance properties for adequate for proposed compositional analysis. These three invariance properties: the perturbation invariance, which is the distance for any perturbation z, the distance between the x perturbed by z and y perturbed by z is equal the distance of the original vectors. The permutation invariance, it is the permutation, if you have a permutation matrix P, the distance between the perturbed vectors, permuted vectors, sorry, is the same of the distance of the original vectors. And the power scaling, that says that the distance between the power of the two vectors is proportional to the distance between the original vectors. Besides these invariance properties, you want a distance that has the standard properties, positivity, symmetry, and triangular inequality. And the distance that to it is the Aitchison's distance, presented here. It's some complicated form to see. We can write alternatively the distance like this, and it is similar to a standard deviation of the log of the ratio between the components of the vectors. And this L is the mean of these log ratios here. We use this distance to compare the treatment groups. We want that the groups are similar, and we want that the distance is as more as possible. To present our haphazard intentional allocation method, we will come back to the example. We have OCG patients, and we want to allocate these patients in two arms. We have 277 patients. The patients are enrolled sequentially according to the order in which they start the treatment. And the allocation problem consists in assigning each patient to one and only one of these two alternative treatments that we call their arms. And the result is the profiles in the alternative arms remain similar with respect to some relevant patient factor. Here we have the current patient's age that will have three classes here: under 30 years, between 30 and 45 years, and over 45 years. The treatment history, it is a very important factor. We have 3 classes here. The first one with the patients that have no previous appropriate treatment. The second one, one appropriate treatment without response, of course, because the patients needs treatment yet. And the third class, 2 or more appropriate treatments without response. The third factor that we consider is the severity of the symptoms of OCD. That we consider here with 9 classes, and this class is based on the score of the Y box, that is a scale to evaluate the severity of OCD. And the last factor is gender with 2 classes. Now we need to introduce some notation. We have these vectors NIA, NIH, NIV, and NIG. The vector of the quantities of patients already allocated to an arm I belong to each category of factors, age, history, severity, and gender. For example, to age, we have 2 categories, and N1A is the focus of each classes of age in the RB1. We want to consider to the sample size in each arm, because we want that these arms have approximately the same number of patients. And you build a vector with the sample sizes in one another group. Okay, for example, N1Z is the number of patients in the arm 1 and the number of patients in the arm 2. Okay, and the complete profile of arm I is the concatenated vector like this, with the quantities in each factor and the sample sizes. And in order to avoid the empty categories, we consider here a weak prior, like a vector like this, where each one of these vectors is 1 divided by the number of classes, the number of categories in each vector. Okay? And now we consider the quantity vectors N and the prior W, and we will construct we build a regularized proportions vector that is the closure unit transformation between the frequencies and the prior for each factor, or age, severity, and so we will define a heterogeneity measure between arms 1 and arms 2 by this function, the distance between the vectors of age, the Aitchison distance between vectors of age, history, severity, gender, and sample size, the mean of this distance, and we need to minimize these quantities. We will consider that a new patient enrolled to the study must be allocated to one of the 2 arms. We will denote by X the vector of the binary vectors indicating to each category the new patient belongs to each vector. Then this is our algorithm to allocate the patients. It's for each J in one 1, 2, we consider the allocation of the new patients X in arm J. That is for I in 1 and 2, we'll sum this vector of the patients to an arm, performing these steps for each arm, and you allocate the patients in the arm that minimizes the epsilon perturber distance. I will talk about this now. Then the steps is construct the regularized proportions vector for each factor and for each arm. We'll construct a random vector BI with components UI and 1 minus UI, where UI are independent generated by a uniform 0, 1, and the epsilon perturber distance is the 1 minus epsilon plus the heterogeneity measure plus epsilon times the distance between the two random vectors generated here. We can interpret this measure that distance between groups plus random effect here. Thanks. We allocate the patients in the arm that minimize this perturber distance. To illustrate our method, we will consider some numerical experiments. We will vary the epsilon in this range, 0, 0.005, and so. And we will generate 300 permutations of the original data to represent possible sequence of patients arriving at hospital. And for each permutation, we run the pure random method and the haphazard allocation method for 300 times. And we have two performing criteria to evaluate our method. The optimality, based on the distance, we want the groups more similar as possible, and the benchmark here is deterministic intentional allocation scheme with no random component. And the second performance criteria is the coupling based on UDQ coefficients, concerning the definition of tendency to allocate each pair of patients to same arm. The benchmark here is the pure random allocation method. The epsilon equals 0 is equivalent to intentional allocation scheme with no random component, and epsilon equals 1 is equivalent to the pure random method. Then here we have a heterogeneity measure delta between arms. This is the percentiles, 5, 25, 50, 75, and 95% percentiles, computed by 8 Haphazard allocations, the 300 allocations, and this bar represents the median of the percentiles, and this vertical line corresponds to 5 and 95 percentiles, and this continuum horizontal line represents the median distance for the deterministic intentional allocation method, and the percentiles with 5 and 95%. This variation occurs because the permutation of the order in the patients. because the deterministic intentional allocation is the same for the same order of patients. And the UDQ coefficient, we want that the UD coefficient is similar to Puri-Randall method. Here we have the quantiles again, and we can see that the for epsilon lower than 0.05, we have results very similar to the Puri-Randall method. Okay. Here in the distance, the small values of epsilon is more similar to the intentional allocation. Well, then the final remark is with appropriate calibration of permutation parameter epsilon, the Haphazard intentional allocation method proposed in this work is has the recurrent property of being able to conciliate the performance on optimality accounted by deterministic intentional allocation with the performance on the coping accounted by the Puri-Randall allocation method. And as we see in the figures, for epsilon lower than 0.01, the optimality acquired by our method comes close to deterministic method, and the epsilon greater than 0.05, the coping acquired by our method is very close to Puri-Randall method. This is some reference. Thank you.